Hello everyone, I'm Janvi. So today our topic is regarding the subject IoT, development of an IoT platform for smart campus. This presentation outlines the development of an innovative Internet of Things platform designed to enhance the safety and efficiency in smart campus environment. The platform focuses on real-time monitoring of indoor air quality, specifically CO2 levels, to address the challenges posed by airborne transmission of viruses. Introduction. The COVID 19 platform highlighted the need for proactive safety measures in public spaces. Educational institutions were particularly impacted, requiring efficient monitoring of indoor air quality. Objective. The primary objective was to develop a robust IoT platform for real time monitoring of environmental parameters, focusing on CO2 levels to mitigate the spread of airborne viruses and enhance the campus safety. Need for IoT platform. Pandemic response. The transmission of SARS and COVID through aerosol emphasized the importance of monitoring indoor air quality. Studies indicated that elevated CO2 levels correlate with poor ventilation, increasing the risk of airborne transmission. Focus on CO2 monitoring. CO2 concentration serves as a reliable indicator of ventilation effectiveness and air quality in closed spaces. The platform aims to provide real-time data to inform ventilation strategies and to ensure compliance with health guidelines. So what are the challenges faced? Interoperability and data management. Diverse IoT devices from various vendors often use different communication protocols and data formats. This poses a challenge for seamless integration and communication amongst devices. Data management. The platform generates large volume of data that need to be processed and analyzed in real time. Traditional databases may struggle with time series nature of the data. Solutions are interoperability and data management. One of the major challenges in IoT based healthcare system is the lack of standardized communication protocols among various devices. Implementing a centralized middleware such as Home Assistant helps overcome this challenge by acting a bridge between different communication protocols like Zigbee and Z-Wave Bluetooth. This allows seamless data exchange and device coordination, enabling different healthcare devices to work harmoniously in a unified ecosystem. This results in bigger integration, automation, and control over medical devices, ultimately enhancing patients' healthcare. Data management. Efficient management of large scale real time data is a common issue, especially when dealing with sensor networks in IoT systems. Using InfluxDB solves this problem by offering scalable time series database optimized for high performance data writes and queries. It's designed to handle large volumes of data with minimal latency, making it ideal for applications where timely decisions are crucial, such as monitoring applications where timely decisions are critical, such as monitoring a patient's health. InfluxDB's architecture allows for efficient storage and retrieval of time series data such as sensor data from medical devices, which can then be visualized and analyzed using Grafana to provide actionable insights. So the system architecture for these implementations would be: the architecture comprises various sensors connected to a centralized IoT platform. Sensors collect the data and transmit it to the platform via wired or wireless connection. Middleware solution. Home Assistant was chosen for its extensive community support and ability to integrate with wide range of devices and protocols. It facilitates interoperability and allows for easy device management through a web interface like an web application or just an application or a website that would help in navigating through all the features that is being performed by the sensors and to access the relevant information. So the tools used are: Grafana is a popular open source platform used for visualization matrix. It excels in providing real-time data monitoring by enabling users to create dynamic customizable dashboards that reflect key performance indicators and trends over time. In healthcare, for example, it can be used to track patient vital signs, medication administration, or operational data in hospital management. Grafana's flexible nature makes it compatible with a range of data sources, including databases like InfluxDB, making it a powerful tool for data-driven decision making. Node-RED is a flow-based development tool that simplifies wiring of devices, APIs, and online services for IoT. It allows non-programmers to set up a complex automation workflows triggering action based on data received from sensor or other devices. For example, if a patient's heart rate surpasses a defined threshold, Node-RED can automatically send an alert to healthcare staff, streamlining the response process and reducing reaction time. It supports integration with other platforms like Grafana, InfluxDB to create seamless data flow and actionable insights. InfluxDB is a high-performance time series database used to store and query data points efficiently. Its ability to handle high volumes of time-stamped data makes it ideal for IoT applications like healthcare monitoring, where frequent data sampling is critical. For instance, in a patient's monitoring system, InfluxDB can store continuous streams of vital signs like heart rate or oxygen level, allowing doctors to visualize trends and making informed decisions in real time using tools like Grafana. Its integration with Grafana enables interactive dashboards and alert systems based on data trends. So here are some real-world applications. University admission exams. The platform was deployed to monitor air quality during exams, ensuring a safe environment for students. Data collected during this period was analyzed to assess the effectiveness of ventilation strategies. Energy monitoring. Integration of solar photovoltaic systems allow for tracking energy generation and consumption, contributing for sustainable efforts. The platform enables real-time monitoring of energy usage across different buildings, helping to identify the areas for improvement. Security and privacy concerns. Importance. Protecting sensitive data collected from various sensors is crucial in an IoT environment, especially in an educational institution where privacy is paramount. Measures taken. Data encryption is implemented through HTTPS for secure transmission, and access control measures such as VLAN and RBAC are utilized to restrict the access to sensitive data. Security audits. Regular security assessments are conducted to identify and mitigate the potential vulnerabilities in the system. Conclusion. Impact. The IoT platform demonstrates the potential of integrating diverse systems for enhanced monitoring and control in educational environments. It provides a scalable, flexible solution that can adapt to changing needs. Future plans include expanding the system to include more sensors and devices, enhancing the monitoring capabilities across the campus, and exploring the integration of machine learning algorithms for predictive analysis. Thank you. I hope the presentation was informative.